Thanks, everybody. Give it up for VM Day, Cartesi, Fuel. So my name's Hans. I'm a developer at Risc Zero. We're a company that's trying to pioneer verifiable computing. What does that mean? Well, we have a virtual machine, hence VM Day, and we verify it with zero-knowledge proofs. Specifically, this virtual machine is built on the RISC-V instruction set architecture, and we utilize ZK Starks to prove that. We do that because the VM itself and the RISC-V instruction set is the circuit. This addresses the growing needs for privacy, as well as security and computational processes in a, in theory, decentralized way. It's ideal for applications requiring data integrity, confidentiality, and of course, that's useful in blockchains, finance, and a number of growing fields. So, how do we do this? Well, like I said, it's a zero-knowledge virtual machine. It emulates the RISC-V instruction set. RISC-V, if you're not aware, is an open source instruction set, recently developed. It's available on consumer hardware in a growing fashion. It's a reduced instruction set. So typically, CPUs are something like x86. These are just really complicated instruction sets. They have quite a few instructions. RISC-V greatly reduces that and allows us to easily implement and constrain the system for zero-knowledge proving. We support languages like Rust. In fact, that's a first-class citizen. It's written mostly in Rust. But in theory, this should work with any compiled language that can be compiled to the RISC-V architecture. There's a growing demand for RISC-V, and we hope to continue to see it grow. And we likely will, especially with the way chips work. Anyway, so the core of RISC-V and Risc Zero, zero-knowledge proofs. What are they? If you haven't heard, well, they're a way to prove data without necessarily revealing that data. What does this mean? Zero-knowledge proofs can validate computations without revealing the data or virtual machine state. We use ZK Starks to provide scalable, transparent, cryptographic proofs. Our design ensures that security is utmost, it's very important, and it allows us to ensure that the validation and integrity of processes carried out within the virtual machine are reproducible and verifiable. It's ideal for applications requiring integrity, so hence blockchains. It's easily integrated and verifiable with our Stark to Snark, basically minifying the zero-knowledge proof with our Banzai proving surface, which is just a bunch of GPUs. So how are we doing this, and how does it affect you? Well, our hope is to streamline this sort of execution. You write familiar code. You don't have to learn a specific DSL. You probably already want to learn Rust if you don't know it. And that's how we do it. There's various methods that go into maintaining the integrity of this. We use a couple of hashing methods to make sure nothing within the pipeline is actually modifiable without causing some sort of collision with the hashing. And so here's an overview. Basically, you write some code in the guest, which is the virtual machine. That's compiled to an ELF binary, put in an executor. Inside of this box is where this execution happens. This middle area represents an execution trace. In other words, what actually happens on the processor, where memory is written to, et cetera. That is proven, and you get back a receipt. So this ensures trust. It ensures computational correctness and integrity. Integrity seems to be a power word today. Verification process, confirms the integrity and correctness of that execution. It's essential for maintaining trust in the system. How is this useful? Well, it's shaping the future of secure computing. It opens a new era. It merges advanced cryptography with open and flexible standards, that is RISC-V. And it addresses the critical need for security and verifiability, as well as privacy in the ZK setting and context, which is incredibly useful for blockchains and finance and healthcare and any other sort of data-sensitive sector. So what are some of the challenges we have ahead? First, hardware requirements. Proving things is demanding. We have Bonsai. That's our proving service. It's a bunch of GPUs. It's not exactly cheap, but it's worth it. Virtual machine performance. Right now, the VM, the ZK VM, runs in the megahertz range. We'd like to see that in the gigahertz range. We're also constrained by memory. It's nowhere near as performant as your laptop or possibly even your phone, but that's improving day by day. RISC-V adoption. Well, RISC-V is an interesting thing. It's certainly being more adopted. It will take some time, though. Language adoption, package support, and developer tooling. Basically, learning Rust, learning other compiled languages, probably worth the effort. But hey, decentralization hasn't been a priority for Risc Zero, but it's important. And of course, getting the word out. It's up to us to spread the word that these things are possible. You can use these snarks on-chain for verifying things on-chain. So it opens up a whole world of possibilities. Anyway, that's our QR code. Scan it if you'd like to have some more info. We look forward to your questions. Thank you.
Does anybody have any questions? I can bring a mic to you.
What are some of the use cases or applications you're currently seeing an interest from for using Risc?
Yeah, so the applications are pretty vast. I mean, you write normal code. You're not thinking in circuit languages. You're not thinking in special DSLs. You're not really even writing code that you would think needs to be in a ZK proof. You just write normal code. And that's pretty amazing. Because you can basically co-process all of that code off-chain and then post that back on-chain and verify that on-chain using Groth 16 verifier with the start-to-snark pipeline I mentioned. So it allows you to remove computation from on-chain, which is, of course, expensive and gas-intensive, and still have that in a verifiable way that anybody can verify. So if your program runs in, let's just say it's a really complicated program, you don't necessarily want people to have to rerun that either. So they can just verify the proof, sublinear time, and it's pretty useful, especially when you want to put stuff on-chain. We have a couple of applications that we've actually developed in the last couple of days that demonstrate this. You can check it out on our website or Twitter. And one of them is Bonsai Pay, and it's using the Bonsai proving service to generate proofs that are verified on-chain so that way you can send crypto to your email address effectively. It's pretty useful. It unlocks a whole world of possibilities. Anyway, next.
Cool, thank you. One question, if I want to run a Bonsai prover myself, how much GPU do I need?
Well,
Or how little do I need, maybe?
You can run it off of your probably consumer-grade laptop. There's a time constraint here, though. People don't like having to wait hours. So the Bonsai proving service runs on anywhere from 50 to 100 GPUs. I don't remember the exact GPU model, but that usually reduces a few billion cycles down to a couple of minutes.
Okay, we have time for one last quick question.
I'll make it quick. So compared to a DSL, if you write your circuit in a DSL, intuitively, I would think that it's probably more optimized.
Yes.
How do you see that for the future of Risc Zero? Do you see that? Because I kind of see that as if you're writing something in production, go write it in a DSL. If you want to do something fast, easy, write it in Risc Zero. How do you, any comments on that?
Sure, yeah. So there's definitely a performance difference, and there likely always will be, but we're focused on general computation. Having a DSL, well, it might be a fully featured language. It's often difficult, and you need specialized people, and you need specialized talent in order to do so. This removes that. I'd say it's sort of analogous to like ASICs versus CPUs. What won in the end? CPUs.
Okay.
Yeah.
I think we have to wrap it up. Thank you so much.
Sure thing.
And we'll see you on the panel
Thanks,
after
everybody.
the lightning talks.
Thanks. Then keep on the applause, please, because we got Kautuk with Stackr. You're going to tell us something about the next generation of virtual machines. There you go.
Hello, everyone, and yeah, thanks so much for having me. Just waiting for the slides.
We need some elevator music. Do, 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 do. Only the Americans get that. Okay, there we go.
All right. Yeah. Hey, everyone, I'm here to talk about Stackr. So we're building a micro rollup framework that allows scaling Web 2 and Web 3 applications. So before we begin, everyone talks about like where the rollup is deployed, what exactly is a rollup, are rollups real or not. But I want to start with like why is a rollup? Like what is the purpose of rollup? Why are we even building rollups? So a little bit about me. So I'm the founder of Stackr, and so the first generation of blockchains, which was Bitcoin, focused mostly on settlement in terms of asset transfer. Then came in Ethereum, which added another layer on top of it, which added arbitrary execution. However, the problem with that was the execution and the settlement was a lot coupled, was very coupled together. So they formed monoliths, and that caused all the scaling problems. So one could not scale without the other, and all of the other things like it was not that we had a lot of demands when it was invented, but now that we are getting a lot of adoption with all of these things, we definitely need to think about it. So that's where like generation 3 blockchains came in, which goes under the concept of modularism, which is separating execution from settlement. And that is where rollups come in. So the purpose of rollups is to like separate the execution from the settlement so that the application scales and like works better. So there are a few rollup misconceptions. Because of the initial design that we saw over here, a lot of things like got into like how a rollup should be designed, wherein it shouldn't be like that. So a rollup needs to run a VM. So it's ironic that we are at VM Day and I'm talking about like we should not run a VM, but I'll prove the point later. So another thing is like the rollups need to be stateful. So rollups don't need to be that. So you can just like take in some inputs from L1 and then just do some stuff without actually even storing any state. And the other thing is like rollup needs to be a blockchain. That's also not true. So just to go over that, let's take an example of matrix multiplication. This is a seemingly simple compute, like you just like take in a bunch of numbers, you multiply them, and then add them together. However, this gets very complex as the size of matrices grow. So what happens is like it becomes very impractical to do it on-chain. So what's the solution? So let's build a matrix multiplication rollup. So there are just 3 steps. You get all the inputs from L1. You just do the matrix multiplication off-chain, and you just post the results back on L1. And on top of that, you can just do like easy fraud proofs because re-execution is a thing. So you can just like re-execute all the data on-chain, and you'll just do like a fraud proof to check if the matrix multiplication was right or not. Obviously, it's going to cost more, but that's what fraud proofs are. So what essentially is there that you get a full rollup, which is completely valid. There is no VM because we can do the computation anyhow. There is no state because the matrix multiplication rollup doesn't store anything, and there is no blockchain involved, obviously. So what does that mean? This is a valid rollup. So that's anyone can do this. Just take input from layer 1, just multiply some numbers on a calculator, and then post back the results. So rollups essentially become like a message passing bridge, wherein you just do computation and you just post that result back on layer 1. So these are some characteristics which every rollup should have. So they should be flexible. That means they can just there should not be any constraint on input, output, or the state data. They should be deterministic. That every action should have like a deterministic outcome, and they should publish data on L1 so that the computation is verifiable. So what the heck are micro rollups? So that's what we are building. So what the heck are those? Before that, we need to understand what the hell are general purpose rollups. So for general purpose rollups, say run a general purpose VM. The VM has all the bells and whistles that you'd need to build any sort of application. That VM is shared by all the application, and the apps run inside the VM. Then came in application-specific VMs. So these are modified VMs which are responsible for handling a particular set of tasks and only implements a specific feature set, but the apps still run inside the VM. What it essentially does is they kind of follow some of the characteristics except flexibility. Because flexibility is something which these rollups cannot provide, and that's what is because you are constrained by the rules of the VM. So what's the solution? That's micro rollups. So the STF is the app logic itself. It's not that you are running a separate STF for running the application. You just implement the STF as the application logic itself. There are no constraints. They are fully modular because you can do whatever you want, and they're extremely lightweight so that you could run it on your mobile device or your browser window or whatever. So that's, yeah. So to define micro rollups, they are like standalone neo execution environment. So I just love inventing terms. So new execution environments is a term which just came up after micro rollups. And what they do is basically they do local execution and then they outsource verification to some other entity. So the application, instead of running inside a VM, the application becomes your VM or not a VM. So this is a basic micro rollup architecture. So the user, so the micro rollup splits it into two parts, which is the executor and the auditor. So the executor is responsible for just running the application logic. The user directly interacts with the application. It sends in requests and gets a response, which is immediate because this is very similar to how Web 2 applications work. And then the executor takes up all the computation results and sends it to the auditor, along with how the results should be verified. So it takes in the results and a verification mechanism, sends it to the auditor. The auditor generates proof or attestation, so it can actually re-execute the data or just run it inside like a VM or like a Risc Zero VM or like whatever that, and it just posts that data on L1. So that's how a micro rollup looks like. Yeah. So if you remember this, then this is what micro rollups enable. So they can just run any kind of application, send it to the auditor, and then post it on L1. And this unlocks a new paradigm for different kinds of applications. You can build games, cloud services, social networks, supply chains, identity limits. So there is absolutely no limit. So the idea is like you can just progressively decentralize Web 2 applications and make them like decentralized. And that's where Stackr comes in, which is a framework, a toolkit, and a network all built into one. So it provides a framework to implement micro rollups. It provides all the necessary tooling to build micro rollups, and it provides a network of auditors that allows you to post data and sends it across. And this is how the Stackr framework is structured. So you have two layers. One is the execution layer, which has all the applications that run all the execution in their own runtime. Then we have the Vulkan layer, which is aptly named. So it does all the auditing and the verification. It also does proof generation, and it also helps in interoperability between the applications. So the term micro rollup was actually inspired by microservices. So each application can be thought of as a simple microservice, which kind of works together with other microservices or micro rollups to become like a larger application. And these are some of the features. So the application executes stuff in their own runtime. You can build custom state machines as your own app logic. They're completely lightweight. You can have plugins. So we don't enforce anything. You can have your own sequencing layer. You can have your own data availability layer. You can do whatever you want in the entire stack. And the most important thing is it helps in sufficient decentralization. So executors can actually be deployed as like centralized application, and this helps them to progressively decentralize their stacks. So the objective of Stackr is that while it can be used to build full rollups, it does not place the same emphasis on the highest level of security guarantees or permissionlessness. Instead, it enables halfway house level of security, which was also noted by Vitalik in his blog post, so that it helps like onboard a lot of Web 2 application into the Web 3 space. And yeah, we are excited to learn more about like different kind of use cases. So please hit us up. The developer preview of the SDK and white paper is coming soon. And you can use this email to reach out to us. Yep. Thank you.
Thank you. OK, do we have any questions?
This is pretty awesome. Yeah.
Thanks.
So you mentioned that it doesn't, so micro rollups don't put an emphasis on the security aspect of things, right? So the first question is, what particular use case do you see being for micro rollups? But also wanted to get your take a bit more on the differences in utility between a micro rollup and perhaps the quote-unquote L3s.
Yep. So, like I said, like it's not that we don't put any emphasis on security. It's just that we post some emphasis on security. Like it's the case that it does not inherit the full security from L1, that you are running all the fraud-proof mechanism on L1. The verifier committee, which I mentioned, I think. Okay, it stopped working. But yeah, the Vulkan layer which I showed up is the one which is responsible for verification. And it is the one which recomputes or like generates proof, and that's responsible for creating a sovereign system. So that's what I meant by security. And for the use cases, you can technically build like any kind of use case. So let's say, for example, you're building a game, and the game requires like a very high tick rate. So you can build the execution environment, which is very high throughput environment. And then once that session is over, you can actually demarcate the entire session into chunks of time, and you can just post like a 2-second data or like a 5-second data stream of stuff on chain. So that's how that's one of the use cases that you can actually build.
So the plugins thing looked really cool, but this means that if I'm building the plugin, I also have to build a verifier for it, right?
Sorry, what?
If I build the plugin, I also have to build a verifier for it. Otherwise, it's like untrusted execution, right?
Yeah, so the plugins are actually like wrappers on top of the base environment. So the base environment itself is something which the verifiers can prove. So we are building a whole execution pipeline. So it takes your code, it divides it into like executable packets, and then just run it through like a prover. And that's something which you are already building. So anything that is built on top of it is automatically like verifiable. So that's what we are doing.
So we have a VM.
Not at the execution side. Yeah.
So the auditors are actually doing quite a lot of work, I guess, in order to generate these proofs. So how is the fee market is going to look like for these auditors?
Yeah, so that's an interesting one, because when we are thinking about it, since it's a hybrid sort of system, so it has components of Web 2 and Web 3 both. So we kind of divide the network into two parts. So the user and the application becomes one economy on their own, and the application and the auditor becomes an economy on their own. So the user and the application lies in the Web 2 sort of economy, and the application and the verifier comes in the Web 3 sort of economy. And that's where the fee market is there. So the committee, it's something which we're still like researching on what's the best optimal fee economy would look like. But yeah, that there would be some sort of like a fee market, or like some sort of like a fee market. Yeah.
Okay, any other questions? Okay, if you can't tell, we're killing a little time because their speaker is on their way. Okay. All right. Do you have a question, Mitchell? Okay. Cool. Thank you very much.
Yeah, thank you so much.
Thank you. Just give us 1 minute. We're locating a speaker. Flights, right? So do they.
So it's going to be a race between Rushi and Dimitri. Who's going to be here first to do the next presentation? I guess they were both stuck in traffic, as we all know by now. Let's give them a big round of applause when they run in. It's Rushi. Welcome, welcome, welcome. Here's your mic.
No, I'm good. So what happened is they booked me for 3 back-to-back panels. The first available one got pushed back, and Celestia one got pushed back. So I'm everyone's problem now.
I'm going to give you 6 minutes.
Yeah.
Then you got 2 more minutes.
That's all I need. All right. I'm here to talk about next-gen virtual machines. So last year, we saw $3 billion lost in smart contract hacks. That number is up to $4.2 billion. The problem in execution machines and next-gen blockchains is pretty clear. You probably want to deploy your smart contracts, deploy your Curve on Aave, Uniswap, whatever, but it's getting hacked every year. The most common bug in today's blockchain ecosystem is re-entry. You deploy a smart contract, thinking it's all good, there's integer overflow, and bam, the next day you lose millions of dollars, if not billions, right? Move is built by Facebook. For those who aren't familiar, poured $1 billion of research, developed an Aptos and Sui, built-in bytecode verifiers, interpreters, whatnot, to make sure that when you do deploy smart contracts, it's done so in a secure and fashionable way. There's also some comparisons between Solidity, Rust, and Move. If you guys are developers, this is probably the most commonly known languages, but Move is built to have security at the forefront. So when you execute a smart contract, it actually has formal verification built into the VM itself. Formal verification is typically a principle that's built into auditing firms, right? So when you pay an auditor $100K a year to audit your smart contracts, they check for, hey, does this code have integer overflows? Does it have byte mishaps? What Move is actually really special for is it happens in the VM itself. So there's embedded verifiers, provers, so when you execute a smart contract, it says, hey, is there integer overflow? Is there like a flash loan attack that could possibly happen? All these embedded protections so that when it does finally execute, it's fully clear. It's around 90% of bugs that are fully covered with Move provers. So a little bit about what we're doing and where we are. Near just announced their DA, so that's kind of where it's come from, NearCon. But we essentially have all these different DA layers that's kind of building up into here. And this is kind of our tech stack. So right now, we're seeing a huge rush in execution layers where anyone can use whatever VM they want. We saw Eclipse launch with the Solana VM. We saw the Fluent guys launch it with the Wasm VM. And now we're coming to market with the Move VM, built by Aptos and Sui, obviously. But now we're bringing it to Ethereum in an Ethereum native way. So first off, starting with the M1, which is a decentralized sequencer. Biggest problems we see at the Arbitrum base right now is with a single node, there's large points of failure. Now with M1, you can use 100+ nodes, have decentralized sequencing that's actually economically incentivized. So you can stake your native token, you can launch your own native token, stake it as well, and spin up your own rollup using the shared sequencer, using Ethereum settlement, using whatever DA choice you want. In this diagram is near DA. We're announcing Celestia, Eigen, and Avail partnerships later this month, which is why I'm all over the place. And use whatever VM you want. So we're fully Aptos compatible, Sui compatible, and the actual benefit is that we're fully EVM compatible. So obviously the issue with next-gen chains is cool. You have this cool virtual machine that requires a programming language, but everyone writes Solidity, everyone writes EVM code. So the question is, how can you get Curve, Uniswap, Aave, these big blue chip protocols, as well as the average Solidity developer count to use next-gen VMs? What we did is we built a transpiler. So anytime you launch a Solidity code, it transpiles out a Move bytecode and launches on the virtual machine itself. I think the biggest issue we see in execution layer environments is everyone's like, cool, the EVM sucks, but no one wants to do anything about it because it develops like the entire mindshare and the whole roadblock is everyone writes Solidity. So how can we scale Solidity while leveraging Ethereum settlement? And that's the kind of architecture we're bringing. The modular Move VM that's fully EVM compatible, that uses the Ethereum settlement, that uses whatever DA you want. The cheapest and most efficient rollup on the market today. A little bit about more performance and more benefits of Move. For you gaming nerds out there, Move is built with gaming in mind with a concept of dynamic NFTs. Right now, if you look at a first-person shooter, you've minted 1 million NFTs when you're killing 1,000 zombies. Whether it's some mag upgrades, you're changing the caliber. That's a lot of different state changes that lead to new minting NFTs, which can often clog up the network. If you look at DeFi Kingdom and Harmony, they actually broke the Harmony chain because they're doing so many transactions. So next time this bull cycle comes, which hopefully is soon, these gaming protocols that have raised so much capital are going to be minting millions of NFTs. With dynamic NFTs, with the Move VM, you can actually swap out traits as well. So if you kill 1,000 zombies, if you kill 2,000 zombies, you can swap out the mag within the smart contract itself, so you don't have any of these gas issues that you see with gaming contracts. Second thing is designed to be modular, where it's on Ethereum settlement, Avalanche settlement, BNB settlement. You can bring the Move VM to every system with modularity in mind. And last thing is parallel processing. It's pretty much a Solana thesis in speed, speed, speed. Eclipse brought it to market in a modular native fashion. We're going to be the same thing. We notch 146,000 TPS, bringing parallel processing, specifically the DMBFT, to the Ethereum settlement and modular thesis. A little bit of Fractal, which is the EVM compatibility. That's kind of where our niche is. So the biggest issue I touched on with next-gen VMs and execution environments is how do we get Solidity developers using this? So the transpiler is pretty cool because we built a mapping system. So essentially, Solidity has 146 opcodes, Move has 54 opcodes, which is why it's generally more secure. When you deploy these Solidity smart contracts, it breaks it down to the 146 opcodes, takes it to YOL, which is a more of an intermediate language, and then maps it to the Move opcodes. I won't get too technical, but long story short, you can communicate your existing Solidity smart contracts with the Move provers and launch on which machine. So you can actually use Move as a feature, not a requirement, which is how we actually see the adoption of these next-gen virtual machines. Solana just unveiled the Solang, which is the Solidity module. This is very similar, except it kind of prioritizes it, and it's done at the SDK level itself. The benefits here is you have full EVM compatibility. So if you're a current game written Solidity or EVM, you can now parallel process. You have 146,000 TPS built in, and you actually have built-in formal verification. So all the struggles that you've seen with Solidity, we all saw the curve attack and how bad that was. We saw the DAO attack. We saw pretty much every attack that's crippled DeFi in today's economy. Now can be prevented with a 90% success rate and actually increasing to near complete success rate with these built-in provers. A little bit about where we're at. Right now, we're compatible with every single DA solution, including the new Near DA that was launched. We'll be compatible with Veil, EigenDA, Celestia, the bigger names in the industry, as well as our mainnet solution will be a fully compatible ETH-L2 that leverages Celestia for DA and has MoveVM as well as alternative VMs for solutions. The network itself is where we have our mainnet, as well as we have a few great clients, both in DeFi and gaming, launching their custom app rollups, all connected to the shared sequencing network. The problem with traditional RAS models and launching rollups is, sure, you have 900 different rollups, but there's no way to connect them all. By having a unified shared sequencing network, A, you can now make sure that you have one network that doesn't have downtime issues, but B, you can easily move liquidity from point A to point B, kind of creating a unified experience. And second thing is making sure the community first. We've all seen those tokenomics of those L1s I won't name. We're actually going to be community first, making sure that majority supply goes to the community, whether it's developer incentives, making sure the validators are getting proper yields, making sure that we're transparent in everything we do. And yeah, it's a little bit on the Move stack, which is how you can leverage the execution environment. It's the first execution layer environment focused stack where you can use whatever DA, use whatever rollup stack, but we're actually focusing more on the VM itself. We do this through a revenue sharing model, which I'll get more into a later point, probably in the panel. But essentially, you can use your VM, use whatever stack you want, and launch your Move rollup at will with composability built in. And yeah, I'll get more into the dApp partners because I know my time is wrapping up, and then we can get into the partners. What we've seen is actually a lot of organic growth, both from the EVM side. We've onboarded some of the bigger NFT marketplaces, DeFi protocols, launching natively on the ecosystem. We have a lot of Cosmos protocols building on top of us, like Shellgrid Finance and the latest Binance Accelerator, as well as onboarding the top 5 Aptos and Sui protocols, and kind of being a hub of all these different chains. So you have Move development, you have EVM development, and now you have Cosmos development, since we're fully IBC compatible. Kind of be a melting pot of all 3 ecosystems. And yeah, I think that's my time. Thank you guys so much, and sorry for being late.
Okay, thank
Questions?
you. What an entrance. Very New York.
It's the East Village of me talking.
Do we have any questions? Questions? I guess it was pretty self-explanatory. All right, thank you so much. We'll see you on the panel.
Then another round of applause, please, for Dino and Dimitri. Fluent.
So we're going to introduce Fluent. We're introducing Fluent. Fluent is a general purpose execution layer for Ethereum. Our kind of broader idea behind this is that there are, 25,000 or so developers in Web3 today, like 25 million developers in the world, and we believe you should go to where they are. Don't make them have to learn all these blockchain-specific details. And we're building a product that will just bridge that gap.
Okay, so what is Fluent itself from the technology point of view? Fluent is, as Dina had just mentioned, is a general purpose execution platform for WebAssembly languages. And the key feature of this is that it's designed itself on being executed on the WebAssembly itself. So all this is possible because we have our framework. We call it a Fluent base. So what is Fluent base itself? What's the idea of the Fluent base? So Fluent base is a framework that where you can upload your WebAssembly binary, and it is used to embed different extensions, shortcuts, and you can produce proof for this. So it automatically embeds things like our virtual machine inside, also algorithms when the circuit that are required for the proof creation for all virtual machine transitions. Also, it has SDKs for creating apps using different so-called adapters for different languages, for different even high-level SDKs. Also, it has circuit extensions that are required to use to optimize some sort of VM computations, for example, for running keycheck functions or Poseidon functions and etc. And also it brings a set of ahead-of-time compilers that brings support of WebAssembly and the EVM support. Of course, all this possible because we have our own virtual machine inside that it runs using WebAssembly, but actually it doesn't run WebAssembly directly inside. What's the key problems of the WebAssembly itself? I'd say it's not even the problem of the WebAssembly. It's more like a problem of all existing CPU-designed architectures, because everything we have today, right now, it's designed for CPU computations that are full of binary operations, and it's not friendly with any type of curve operations. So the key problem of the WebAssembly here that limits execution a bit is that it has a bit overcomplicated binary structure that is full of relative offsets inside, and sometimes it's quite hard to prove things like doing call operations, doing operations like break between different positions in your bytecode. And for example, if you have a very, very big WebAssembly binary and you need to execute only one small part of this, you need to upload your WebAssembly binary entirely and create proof for the hash verification to parse all sections inside that is full of variable elements, and it's quite hard to prove. It requires to have a lot of gates inside. So what we do is we bring RWASM. We call it RWASM right now. It means that the reduced WebAssembly. So the idea of RWASM is it's 100% compatible with original WebAssembly form standards. So it doesn't mean that this follows binary structure of WebAssembly, but if you take any of existing WebAssembly binaries, you can translate to RWASM without losing any type of compatibility. So 100% of all features from WebAssembly are supported. Also, we run official WebAssembly specification tests, and it shows 100% coverage of all WebAssembly functionality. So what is RWASM? RWASM is a reduced WebAssembly that brings a reduced instruction set of the WebAssembly. So to simplify, it's just intermediate representation. But its intermediate representation has a binary structure that is also optimized for the Poseidon hashing, for doing multiplications on the curve operations. So and also it, of course, doesn't have any sections inside. So we entirely remove all sections, and we honestly remove entire WebAssembly structure by keeping full backward compatibility with the original structure of, with original features of the WebAssembly. So, and the thing that we embed RWASM inside the Fluent-based framework, and Fluent-based runs RWASM. Also, we embed our framework, execution runtime inside execution runtime itself. So if you run some execution flow, you can run like some sort of contracts. You can run some different types of applications. And we also support, as I mentioned before, ahead-of-time compilers that can be used to translate your original binary from EVM structure, from WebAssembly structure, to our special reduced structure. And you can run this and prove without any additional computation overhead. So the only thing that is required, honestly, this is the key goal of the Fluent, that you can, it has internal tree structure, and it stores information about your execution binary, and you can upload any type of binaries, and it automatically translates to the optimized version, and it can run without any additional overhead. And if you want like to call the contract, to call your application, to interact with your application somehow, no matter what size of this application, how complicated the structure is, you can. There is no need to load, to upload your WebAssembly binary and parse it and verify entirely, because our intermediate language is designed to have more like. So you can easily upload the binary and run. as is without any additional validations, verifications, and etc. So this is the idea of the Fluent that has Fluent base inside and have RWASM inside. And also one thing that we optimize for the RWASM that is also very important is how you interact with external modules and external functions. Because if you want, for example, embed some circuit accelerated extension inside your binary, you need to put special item into your section. You need to parse. It has UTF-8 encoding inside. That is quite a bit hard to prove using ZK. And also you need to prove all relative offsets inside. That is a bit overcomplicated. So we also optimize this. And we reduce all these computations to only one instruction and only one lookup element. So you can easily look up the existence of this special optimized circuit for your function. And for the regular developer, it looks like a developer just invokes some function that he or she imports into the model. And we're going to provide a set of optimized circuits. We call it like extensions or external circuits, and you can embed different circuits. So what is an example of such circuits? We can bring support of things like, honestly, we already have partial support of VASI execution environment, so you can compile your glibc applications. Also, we have support of ZK trees. We have support of Merkle-Patrizia trees. Also, we have embedded RWASM itself, so RWASM can prove its instruction itself inside without any additional overhead or additional computation costs. And also, we're going to bring all extensions for the creation of the Ethereum apps. So like everything that refers to RLP encoding, you can do using only one function, and it automatically replace all your computations with our circuits. Yeah.
So how much time do we have? Are we over? Q&A? If there's any questions, we'll take them. If not, I'll probably ask Kim some questions to clarify some things.
Okay.
Yeah, how does this compare to Polkadot's WASM or other implementations of WASM on blockchains?
Like what specific implementation of Polkadot WASM? Do you mean WASM interpreter or what specifically?
I don't know that much about WASM, but the WASM that's used to write Polkadot smart contracts.
So yes, WebAssembly is just a standard, and we here strictly follows WebAssembly standards. It feels like that Fluent base is something like a substrate for the Polkadot, but we don't support Polkadot structures. We don't support Polkadot host SDKs, but the key feature of the Fluent that we can embed Polkadot native functions inside Fluent base. And if someone wants to run ZK optimized circuits using Fluent base, we can just develop a special set of extensions and SDKs for the Polkadot, and we can bring almost native support of the circuits into the Polkadot, into the Fluent base to bring support of the ink contracts, for example, or even running the substrate. So using Fluent base, you can build ZK substrate, for example.
And just to add on that, like the way we think about what we're building in comparison to kind of some of the other WASM approaches in the space and history is, I mean, we kind of separate it and say like, okay, there's like the consensus part of things and social layer part of things, and then there's like the execution part of things. And we think that like execution was always like a good idea. And I think what's really the best way to implement it is in kind of like a permissionless sense in a layered architecture on top of like a consensus layer and a social layer that's already gained like escape velocity. And yeah, that's kind of how we think about it. Any other questions or any more time?
We can do one more question.
Do you have an estimate of how much your WASM binary sizes increase when you translate to RWASM?
Actually, it increases because we align all instructions with field elements. Right now, we consume around 9 bytes per one instruction, and the size of this is always fixed. It is required to simplify the circuit for the Poseidon hash verification, so we don't have to spend additional columns in case for the verification of the field input for the Poseidon hash. And so it increases right now, but at the same time, we did several measurements. For example, one transition cost for the EVM cost around 1.2 million instructions. In our implementation with the optimized translation, we have only 0.5K instructions. So it can bring us up to 2 or 3 times optimizations. Of course, it's not like, it's only about a number of instructions, because under the hood we run our circuits, and so like it's something it feels like a programmable scroll, or for example, programmable ZKVM. If you take the code base or the PSE of the scroll and you modify this, you also need to modify circuits. So here you can prove all transitions from one circuit to another circuit using WebAssembly language. And you can use any of existing languages like Golang, Rust, and etc.
Thank you, guys. Dino and Dimitri, give them a round of applause, please.